What is ionization energy? Well, to give you the textbook definition, it's the quantity of energy required to remove an electron from an atom in its gas phase in the ground state. So what does that mean, right? So first off, just to make it super simple, if we look at this planetary model of an atom, this is beryllium. It's got 4 protons and 4 electrons. And as I mentioned in my previous videos, this is not an accurate depiction of what an atom looks like, but it's a good way for us to understand this in a simple way. So if we look at this, it's just how much energy does it take to remove one of these electrons, okay? And so we have the nucleus is positive. There's 4 protons in the nucleus in the case of beryllium. There's 4 electrons. And if I'm going to rip one of them away, remember, electrons and protons are attracted to each other. Just like the north pole of a magnet and the south pole of a different magnet are attracted, well, positive and negative are attracted as well. So the thing is, what's all the extra stuff here, right? Well, the idea is some elements are solids at standard conditions, some are liquids, some are gas, and basically in order to ionize the element, the atom, we have to have it in its gas phase and then add some extra energy to remove one of those electrons. So we just want to level the playing field so that we're not starting off with something in its solid phase, then we have to heat it up to a liquid, heat it up to a gas, and then add the extra energy to ionize it. So we're just saying bring everything up to the gas phase, but don't have the electrons excited yet. They should be in their ground state electron configuration. And now how much more energy is required to get that electron to pop off, all right? So now let's talk about the trend. And, very typical questions would be like, which of these elements have a higher ionization energy? And so if you saw my video on atomic radius, I mentioned that I believe it's the most important periodic trend because using the knowledge of that and how it works, you can kind of, the rest of it seems pretty intuitive. And so if we look at the periodic table, and this is my beautiful silhouette of our periodic table, the elements, as I mentioned, get larger as we go down and smaller to the right. So they get larger down to the left, right? They get larger as we go down because we have increased number of principal energy levels or electron shells. And so in other words, hydrogen's over here. It has only 1 shell of electrons because it's in the first row or the first period. And then these elements over here have 2 shells. So that's why beryllium, I drew 2 shells of electrons here. And then as we go to the right, the reason they get smaller is because we keep adding protons to the nucleus and more electrons to the valence shell, but we're not adding new shells of electrons. So the increased nuclear charge pulls all those electrons in tightly and makes the element smaller, makes that atom smaller. So now let's tie that into ionization energy. Well, we can kind of simplify it to just thinking about the size of the atom. If the electrons are further away from the nucleus, the force of attraction is going to be smaller. So it's going to be easier to pluck off an electron that's really far away from the nucleus than it is to an electron that's very close to it. So in other words, the ionization energy trend on the periodic table is just going to be the opposite of atomic radius. Since atomic radius increases down and to the left, the ionization energy is going to increase up and to the right as the elements get smaller. Now, there are exceptions. Comment down below if you'd like me to explain some of these exceptions. I mentioned in the atomic radius video that there are exceptions as well, that atomic radius gets larger down to the left, but there are some funky things that happen in the middle. And with ionization energy, there's some interesting stuff that happens in different locations as well. So again, we're just talking in general right now that the ionization energy increases up and to the right. Now, there's multiple ionization energies though. So in other words, how much energy is required to remove the first electron? That's a certain amount. Now, how much energy is required to remove the second electron? That's called the second ionization energy. And you can imagine that as we remove more electrons, the resulting ion that we created has a higher and higher positive charge, so it's attracting the remaining electrons more and more strongly. So ionization energies increase as we increase which ionization energy we're talking about, right? In other words, the more electrons you take away, the harder it is to remove the next electron, okay? But there is something very interesting that happens, which is a spike in the magnitude of the increase in ionization energies. And so if we take an example like beryllium, it's got 4 protons and 4 electrons, right, when it's neutral. So its first ionization energy is going to be a certain value. And now we have a beryllium plus ion that has the same electron configuration as lithium. Then we remove another electron. So, going to the left here, that puts us up over here. And so that is going to be a higher value. But then as we try to remove one more electron, we are now messing up the stable core noble gas configuration. And so the difference in energy from the first ionization energy to the second, and then the second to the third, and then the third going forward is going to be even higher as we try to remove that third electron. So in other words, we remove one electron, now we have a Be+, and it has one more electron in the valence shell. Then we remove the second electron in the second ionization energy. That's going to be a higher value because it's already positive and attracting that electron even stronger. But then we have our noble gas core of helium. And so removing that electron, the next electron, the third one from the third ionization energy, is going to be an even higher jump. This higher jump comes from the fact that the noble gas core electrons are closer to the nucleus than the valence shell. So these electrons are more tightly bound to the nucleus and do not have the same shielding effect experienced as the valence shell electrons. So if we just take a look at the periodic table and we look at some elements, we can figure out which ionization energy is going to have the biggest leap. So now if we look at something like aluminum, well, the first ionization energy brings us over to the electron configuration of magnesium, and then it's going to take even more energy to remove another electron, even more energy to bring us over to here. But then once we're messing up the noble gas electron configuration, that's going to be the biggest leap. So as we remove that next electron, that's going to be the biggest leap in ionization energy. So let me give you guys a quiz, and I want you to comment the answer down below which ionization energy is going to be the highest. But before I do, guys, if these videos help, please give a like, follow, share, save this so you can review it again later. And then if you can consider supporting me over here and patronize me, that helps me to continue making these videos for free. So now my question is, for an element like chlorine, what is going to be the highest ionization energy leap? All right, guys, so comment that down below, and I'll see you in the next one.